So linear independence has a definition and a separate meaning. Just knowing the definition is not enough. So let's say you have three vectors u, v, and w. Then we say the three vectors are linearly independent. Are linearly independent if C1u plus C2v plus C3w equal to 0 can only happen if and only if C1 equals to C2 equals to C3 equals to 0. Okay? The only way a linear combination of the three vectors can be 0, it can be a 0 vector, is if all of the coefficients are 0. So that's the definition. But this definition doesn't really do justice to what it means. So let me try to explain what it means. Often what we want is to have three vectors. Let's say this is in 3D. To be pointing at different directions, okay? Yeah. So that if you take the span of these three vectors, if you take linear combinations of these three vectors for any value C1, C2, C3, you end up spanning the entire 3D space. And the way you say that is exactly this. So let's try to explain, let's try to see why this means that the three vectors are pointing at different directions. That's because suppose you have two vectors here, and a third vector is also on the same plane. Let's say it's still on the same plane, okay? So if it's still on the same plane, then there is some linear combination where, let's say, this new vector here is like C1 times u. So this is u, and that's v, and let's say this is w. Then this vector, this much here, we're going to call it C1u. If this is v, then we're going to call this one as C2v. After all, these are some multiples of the previous vectors, right? Because they're same length, I mean, same direction. There should be a real number that would convert one vector to the other, right? And this parallelogram law says that w is now equal to C1 plus C1u plus C2v, right? But now look at what this is. It's saying that if I move this to the other side, then you have 0 equals to C1u plus C2v minus or plus -1 times w equal to 0. So you have C1, C2, C3, at least one of them non-zero. -1 means it's non-zero. So this example shows that if the three vectors fail to be pointing at different directions, if one of the vectors is contained in the span of the other two, so that it only spans a plane rather than 3D space, then you have something that's not all 0, still satisfying that. Okay, so that's why linear independence is defined like that. Okay?